Right, so today I'm going to show you how to implement a simple Q-learning AI to play the game Tic-Tac-Toe. So the first thing we're going to do is go ahead and make the game and have it play so we can play human versus human, and then we'll incorporate the AI later. So we're going to be doing this in Python. I am using Google Colab, which is this free website. If you have a Google account like I do, you can go on Google Colab. It'll give you a Google server to run your code. Of course, if you don't want to do that, you can go ahead and go to python.org and download Python and run it on your local computer. I'm just using Colab because I think it looks nice. I like that you can run individual cells, like you can see here. So I'm going to be doing it in Colab, but you can do it in regular Python too. The first thing we are going to do is import a couple of packages, and this is just functions that we are going to use later that have already been defined, so we don't have to redefine them. The ones we are going to use are the random library, which is going to help us pick random moves at the beginning, and then NumPy is going to be required for when we're trying to find a maximum of a list. We'll see that later. So to make the game, we are going to use Python classes. And you can think of classes as like a blueprint. It's saying for every example of this thing, like if we have a player class, the player is going to have a name, they're going to have a strategy that they do, and a couple of other attributes, and they're going to have some methods that are like actions that they can take, like make a move or update their memory. And then we're also going to have a game class. So I'm going to go ahead and make the game class first, and I'll give this a comment. Game class. The way that you would do this in Python is you say class and then the name, and I've chosen game. And now we are going to define a couple of functions and variables for our class. So the first thing you always want to do is say the initialize, and this is another reason Colab is cool. If it'll show back up, it sometimes suggests code if it thinks it knows what you want to type. So this function init with these little underscores here is just saying whenever I initiate a version of this game, this is what I want it to do. So I'm going to, whenever I create a game, I'm going to pass in a list of players, and then I'm going to set up some variables here. So I'm going to have a variable called players, and just set this to be whatever I passed in. I'm going to create a board, and the way I'm going to represent my board, our 9 squares, is I'm choosing vertex in range 9. So this is a list, and it is initialized to a list that is 9 things wide of just the empty string, or a space in here. And that's to show no one's moved there yet. And then once we start moving, then we'll of course fill up that array. We're going to have a variable to keep track of whether our game is done or not. We're going to have, and also a winner. So when we finish the game, we will know who has won, and we'll use that information later. Now I'm also going to define a function that's not really necessary, but I like it. It's called printBoard. And then I'm also going to define one that is play game, and this will be the main function for running through the game. And you'll notice I'm always passing in this variable called self, and that is just so when you have a class and you pass in self, that is saying you can reference these variables up here. This method can reference this method. It's just so every method and variable in your class is connected and can talk to each other. And then I'm also going to create a function called check for win. And this is going to be what runs after anyone has made a move to see if someone has won. And then I also like including this one called reset. This isn't really necessary. You can just make a new game object every time, but I like it. And I'm going to go ahead and fill this one in. So it will be just reset the board to range 9. And there you can see it's suggesting some stuff for me to fill in. I'm going to reset game over, and I'm going to set the winner back to nothing. So this reset function just says reset the board, the game is not over, and no one's won yet. So just resetting to what we initialized up here. Okay, we're going to do print board next. So what we're going to do is say, we're going to set up a for loop saying go from 0 to 2, and then print out, you can see their long print statement it's suggesting. I'm going to print out a vertical line and not go to a new line afterwards. I'm going to set up another for loop. It already knows what I'm thinking. And I will actually go ahead and tab to fill this in. So what this says is repeat this 3 times, and then repeat this 3 times each of these 3 times. So this is going to print out a vertical line, then print out the 3 numbers that go to that row in our tic-tac-toe board, and then end it with another vertical line, and then we're going to print a new line. And down here, I'm going to actually change this to be this, just like a horizontal line with a new line at the beginning. So what this should look like is vertical line, the first row separated by vertical lines, and then vertical line at the end, and then a horizontal line, and then the next row, and so on. So it will actually give it the appearance of a tic-tac-toe board and print out what's in the board at that time. Actually, I'm going to open up my whiteboard to explain a couple of other things. Okay, now we're going to get into the main part of our game class, playing the function for playing the game. So we're going to start off with a big old while true loop. So this is going to run forever, and we're going to break out of it eventually by checking if the game is over with this. So we're going to say move equals, and then we want to get a move from a player. So I haven't declared my player class yet, but I'm going to go ahead and assume they're going to have some function called like do move or make move. So I'm going to say players.0 or players, my list of players in the first one, and I'm going to call some function make move, and I need to pass in the board to them so that they can make the move. So I'm going to go ahead and declare this, and we're going to make the method, we're going to fill it out down here when we do our player class. So I'm just going to assume this works fine, and we got some move. I'm going to say self.board, wherever that move is, set it to be an X. We are assuming X, whoever has the X goes first and O goes second. And then we're going to call check for when. And so check for when will look for if the game was won, and it will set this game over variable to true. So we'll say if self.gameOver is true. You can go ahead and say is true, or you can just leave it like this, both are equivalent. Then we're going to break out of our while loop. If not, we'll just keep going and say, okay, do the same thing. And there it's filling it in again. I'm going to go ahead and type it out. Make move. So now the second player, the guy who's in index 1 of our list of players, is going to make the move. And we're going to set his move to be the O. And then again, check for our win. And if our game is over, break out of our while true loop. And then if this isn't true, it's going to keep repeating, and eventually either we're going to have X wins, O wins, a tie, or the board is going to be completely full. And that is it for our main game loop. It's just going to keep getting moves from the players and marking them down and checking for a win. So now we need the logic of checking for a win. And I'm going to go back to my whiteboard here. So the way we are representing our board, you can see here we initialize the board to be an array of 9 elements, which would look like we have 1, 2, all the way to 9. And that's a bit too thick of a pen. What this represents is, if we think of our tic-tac-toe board, I'm going to make this the first move, so it's going to correspond with this first thing in the array, and then fill out the rest of them like this. So I'm sorry, this should actually be an 8. There we go. So what this is saying is, if I have my board here and I say, oh, I want to set the 5th element to be X, it's going to go, okay, 1, 2, 3, 4, 5, and replace this with an X. So when we're thinking of how to check for wins, we'll say, okay, well, we can win either horizontally or vertically or 2 diagonalies. And we're going to need to check all 1, 2, 3, 4, 5, 6, 7, 8 of those. So what I'm going to do is I'm going to make another array conditions. Here we go. And it already knows. That is incredible. And I'm going to actually make them as tuples. So I'm going to bring this down here. There we go. So if I want to look across the rows, I would check if the thing at index 0, at index 1, and index 2 is all the same. I'm going to make this 0, 1, 2. And then for the next row, as you can see, it's already filling them in, so I'll just go ahead and tab over. And what this is doing is it's coming up with every possible way to win. You have the 3 ones that are horizontal, the 3 ways that are vertical to win, diagonal, and diagonal. And if you check with these last two, 0, 4, and 6, 0, 4, it's kind of hard to see, and that's, sorry, 0, 4, and 8. So that is our first diagonal. I'm going to get rid of all this red. And our second diagonal, 2, 4, 6. So that is all the possible ways to win. So then we just need to check all of them. We can say for I, j, k in win conditions. So there we go. And there it's filling it out again. If self.board at I. So if these are all the same, and we have to check, we can actually just do this. Self.board k. If they are all the same, and we also have to check that they aren't empty, because of course we don't want to say you won when the board is just completely empty. So we'll say if they're not a blank space, but they are all the same, then someone has won. We just have to figure out who. So first case we're going to do if it's X. If the symbol we see is an X, then we're going to set the winner. And instead of being text here, I'm going to set the winner to be 0. And that's just letting me know the first player, or the one with index 0, is the winner. And I will set game.over is true. And then just as it's suggesting here, else. So if someone has won and it wasn't the X symbol, then it will have to be the O symbol, meaning the second person has won, and game over is true. Okay. And I'm going to go ahead, no, I don't want that. I can't tab over if it's suggesting something. That was a bit annoying. Okay. But if we don't have a win condition, this for loop is just going to run its course and then exit right here. So nobody's won yet, but we haven't checked if there's been either a draw or if they've filled in all 9 things and still nobody's won. So we're going to say if I don't see a blank anymore. So if blank not in self.board, then the game will be over, and we're going to go ahead and set the winner not as -1 like it suggested, but as 2. And this is just a stylistic choice I'm doing to set the winner as 0 when the first player wins, 1 when the second player wins, and 2 to signify a draw. So if none of these are true, if nobody's won yet and we haven't reached a full board, I'm just going to return nothing. So if none of those are true, game.over will still be false and the winner will still be a blank string. So when I call this up here, see I call check for win, and then I immediately check did it detect a win and thus set game over to be true. And if it doesn't detect a win, it won't do that. All of these are in if statements. So after each move, we're going to get the move, we're going to update our board, and then we'll check for a win, which we'll check and set game over to be true if someone has won or if we've tied. And then if there isn't a win, we will just keep going. If there is a win, we'll break, and we'll know who our winner is. Okay, so we are all done coding our game class. Now we need to make the player class. So similarly, we're going to call this class player and start off with our definition in it. And I'm going to give a couple of variables here. I'm going to give name and strategy. And I'll just say, okay, self.name is the name I pass in, and my strategy variable is the strategy I pass in. The name really doesn't matter, but the strategy is going to be what we're going to differentiate between I want this to be a learning AI, I want this to be a random player, I want this to be a human. So we are now going to define our make move that we kept calling up here. And you can see we're passing in the board, so we need to remember that. We're going to pass in self and board. Now we need a way to print out all of the valid moves, because otherwise you could just, our humans won't know what kind of move they can do. So I'm going to take a minute and make an array called valid moves, and I'm going to say, okay, loop through that board you passed in, and remember, board is going to be some list like this. It's going to be a list of valid places. I'm sorry, board is going to be something that looks like this, not W, where it's just a bunch of blanks or X's or O's. So I'm going to loop through that board and say, if the thing, for each of those things in the board, if it's a blank space, like it's suggesting here, there we go, append valid moves dot append. I'm going to append X. What have I done wrong? Oh, sorry, this should be an if. There we go. So loop through all of these things and look for the blank spaces. That's where we can move. Okay, now we're going to give it a different strategy based on, there it's already suggesting the random one, based on if it's a human or not. So we're gonna, self.human, we're gonna code the human strategy first, and then we will do the random strategy that's suggesting. Elif self.strategy. So if we have a human, it would be nice if we told our human your valid moves are, and then print out the valid moves, and then ask them, where would you like to move? And you don't need this text. If you know what it does, you can just say, give me a move. This thing it is suggesting here in gray that just disappeared, there it is. This is how you can prevent your user from inputting like 2000 as a valid move. You can set up this while loop to say, if the move they inputted wasn't in the list that they could choose from, then keep requesting a move until it is. I'm just going to skip that because I don't believe I will mess with myself. Okay, so we just ask them for a move, we give them their options, we get in a number from the user, and then we return it. And that return move is going to be used up here where we were getting their move in the game. So now if we're not a human and we are a robot, instead we are going to return a random choice from the valid moves like it is suggesting. So valid moves is going to be an array that looks like this. Valid moves will be something like 0, or we could go the third square or the seventh square. So for a human, we'll see this and we'll pick one of those. If our strategy is random, we'll just pick a random one of those. Okay, making sure it didn't mess anything up. And for now, I believe that is all we need for our player. We just need them to make a move. So I'm going to go make sure I haven't messed anything up. Okay. I'm going to go ahead and run. This is nice about Colab. You can separate your code into these cells and then run them individually. Nothing has errored yet, so I think I'm doing good. Now we're going to actually start playing. So when you have these classes, this class isn't a real object yet. We have to define an object using this blueprint we have created. So I'm going to make player 1, and they're going to be a player. I'm going to give them the name player 1, and I'm going to set their strategy as human. And notice I did the name first and then the strategy because that's the order it shows up here when we are initiating our class. Gotta do it in the exact order it shows up. I'm going to give them an opponent, player 2. They're also going to be a player, but they are going to pick random moves every time. I'm going to make a list of my players, player 1, player 2, and make a new game and pass in that list. Back up here, we are defining our game. We need to pass in the list of players. So I'm going to pass in the list of players, and then I'm going to call the function play game. And then at the end, I'm going to print, oh wait, sorry, if game.winner is 0, yeah, there, I can just fill that in. So if the winner was 0, that means the first person, which is player 1, wins. If the winner is reported as 1, that means the second player wins. And if it's reported as 2, then it is a tie. Fill that in. And then we'll call game.reset at the end. So running this, it shows me I'm moving first, so I have all the possible valid moves. I would like to move right in the center, which looking at my board should be move number 4. Red. So I'm going to take number 4, and there you can see it took spot 3, so I can go back to my board. Oh. And we can write something to do this for us. We don't have to keep flipping back to the board. So I took there, they took there. I'm going to take spot 7, and they took spot 2, so I'm going to take spot 1, and I win. I did this. X here, they moved here, so I moved there. There you go. You have now coded a working tic-tac-toe game. And you can actually, if I wanted, I could take out the human and set both of these people to be random and rerun this, and they tied. And I can just keep rerunning this. You can see player 2 is winning a lot. There, player 1 finally ran. Or I could say for x in range 100, do this 100 times. Put this all in the loop. And see, they win about half the time. They tie a lot. So there we go. We have created a working tic-tac-toe game. Okay, I am 21 minutes, not bad. So now we are going to expand this, and we are going to make an AI that learns from itself. And we are going to do this using Q-learning. So I'm going to briefly explain what Q-learning is. It is, you're going to save all of the game states the AI encounters and the possible moves, and then it will remember, did I win when I made this move? Did I win the game where I made this move? Did I lose? And it will assign a reward accordingly. So if I have some tic-tac-toe board, let's say it's playing as X, and this is the game state, then my valid moves array will look like, well, this is a valid move, number 0, and then 1, 2, 3, 4, 5 is a valid move, 6, 7, and 8. Those are all the spaces I can move to, 0, 5, 6, 7, 8. And then I would look at this as a human, we would go, you need to move here, which corresponds to move number 7. So if the AI plays move 7, we'll then give it some reward, some amount of points, and it will go, aha, when I see this state, I know this move gives me +1 points than the other ones. Whereas, say, if it moves, let's say, not there, here, and then O moves here, and then X moves here, and then O moves here, it could think, oh, moving to move number 6 was bad, I'll give that a negative reward. So that's the general idea behind Q-learning. So what we're going to do first is we're going to go ahead and I don't believe we need to make any changes to our game. One thing I will say, if you're struggling to see how valid moves this array corresponds to the game states, one thing that's helpful right here in play game is right before you get a move, you can say print board. And that just lets your human, self.print board. And that just lets your human see the board visually, which is a little more helpful. But if we aren't making changes to our game, I don't think we need to. We're going to beef up our player class. Okay, so the first thing I'm going to do is add another variable called epsilon. And Q-learning, epsilon is a measure of how many times you want to explore and do a random move, or do what it thinks is the best move. So if I have an epsilon ranges from 0. So if I set epsilon like here at 0.3, it's going to do a random move 30% of the time, and then do what it thinks is the best move the other 70% of the time. So the higher epsilon, the more you're randomly moving, the less good you will be because you're just doing random moves, but you are exploring more of the game. So I'm going to add that as a variable here. So yeah, I spelled it right. Okay. And we are also going to add, I spelled it right there, but I didn't spell it right up here. That explains it. We're going to add another strategy. LF, our strategy is AI. And I'm also going to declare the variables QTable, and this we're going to use curly braces because we're going to be using a dictionary. I'm also going to define states, a list of states. So what it is going to do is it will, as we're playing the game, it's going to record all the states it sees, and then once we finish and it knows if it won, lost, or tied, it's going to give a reward to all of the states that led to that outcome. So what we need to do is we're going to need to record the state and then either make a random move or make what we think is the best move based on what epsilon is. So the first thing I'm going to do is create a new variable called state, and I'm going to make this a tuple. And the reason we have to make it the data type tuple is because with dictionaries we can't use lists as keys, but we can use tuples as keys. So that's the only reason. Move index. Okay. So I want to look up, with my AI, I want to look up if this game state I'm seeing is in my table so I can know if it's what the good move is. And here you can see it's already suggesting if the state is not in our table, meaning the AI hasn't encountered this yet, we are going to go ahead and just set it to be 0. So our state in our table is going to be a representation of the average reward we expect for each move. So in our example here, for valid moves, my state could look like this. I think I'll tie, I think I will win, I will definitely win, I will probably lose, and I will tie. And so then if we want the best move, we would say, move 6 is the best move because it has the highest estimated reward. But if we haven't seen the state, we don't know, so we're just going to set them all to be 0. And then we're going to pick a random number, and this is why we need to import random way up here. We're going to say if this random number between 0 and 1 is less than epsilon, we are going to just pick a random move. So we're going to pick a random number between moves, just like that, -1, and then pick the valid move with this index. And you have to do this instead of just picking a random choice index because of the way we've set up valid moves. If we're not picking a random number from our valid moves, then as it suggests here, we are going to pick the move that represents the maximum from our table. So we would go here and say, what is the maximum number? It is 3, so I'm going to pick the 0, 1, 2th, or second thing in my valid moves, which is the move number 6. So this is just how we are getting the appropriate valid move from the maximum number. Okay, and then our list of states, of saved game states we have up here, we're going to add whatever state we're currently looking at, and then finally return our move. Okay, and then we need to add one more function, and I'm going to call this update QTable. And I'm not going to have that. And I need to unindent this one. So once we finally finish our game, we're going to get some reward, and then we're going to go back and update all of our expected values for those states. So I'm going to say for state loop through all my states, and I think I've messed something up. Yeah, right here we also need to include what move we did. So the current game state and what we did there. I think I also need another pair of parentheses. Okay. So loop through every time we had a game state and we picked something, and then say our table at the state we're looking at the action we took, we're going to add whatever that reward is, and then at the very end we're going to clear out our save states. So this loops through all the states we saw as we played our game, and it's going to add that reward to the expected value of the action we took. And then finally, once we're done, we're going to clear them out so they don't get added for the next game and for the next game. And that, I think, is all we need to update player class. So down here, when we're defining our players, we have a new value. I'm going to give them an epsilon of 0.99. And that just says pick a random move 99% of the time. Do what you think is the best move 1% of the time. I'm going to change him to be AI, and I'm going to keep the second guy as a random. Okay, and we can go ahead and run this, and I messed something up. Player. Oh, right. Whenever you make changes, make sure to rerun your cells so they update. It was using the old definition of player. There we go. Okay. And we also need to give him an epsilon, but it doesn't really matter. Okay, so you can see our random guy still beat our AI, but he has learned. And now at the end, if we say print a, what's his name, player1 dot qtable, we don't need to print out player2's. And we can say we can see he saved the game state where nobody had moved, and then he's saving all of these states. And we still need to make him give them a reward, right? So now we have to give them a reward based on if they won or not. So we'll say if player 1 was our AI and player 1 won, then as it's suggesting, we're going to update his Q table and I'm going to give him 1 point for winning. And then say, well, actually, if player 2 was also a learning AI, I'm going to give him, update Q table, I'm going to give him -1 points for losing. And then I'll do the same thing here, but reversed. So if player 2 won, then player 1 gets the negative reward and player 2 gets the good reward. And if they tied, I'm actually going to give them a slightly positive reward, because in this game, ties are bound to happen, and it's more about not messing up and not losing than making sure you win all the time. This also helps them play a bit more defensively if they're happy to tie instead of gunning for the win all the time. Okay, so now if we run and we print out our table again, you see they tied, but now for our very first state, we can see one of the values updated. So it moved the second, it moved here, and found out that's results in a tie. We can go look through our states and see at the very end where it only had one legal move, it still showed that will result in a tie. You can also print out this table a bit nicer. You can say for state Q values in my table dot items, print state Q values. And there you can just see it's putting them on a new line. So here's our state, our tic-tac-toe board represented as a tuple, and then what it thought would happen. So now we're going to train it. So what I'm going to do is say, I'm going to take out these print statements because I don't want it printing for thousands of games. There we go. And I'm going to say, I'm going to define my game and then say for x in range 10,000, play the game and reset and update your Q table each time. And then at the very end, we're going to print out what the Q table looks like. I'm actually going to add a couple more prints. So we run, and there you can see now it's got a lot more states. It played 10,000 games, it discovered all of these game states, and now these look slightly different. It thinks, for example, in this state, it thinks it's going to win if it plays whatever the first move is right there. It's going to tie if it moves here, and maybe lose, maybe tie. We don't know if it moves here. So the longer you let this train, the more and more it's going to learn, and the bigger the rewards are. This update Qtable function we have is not the official one. This is just a simplified version, and it works relatively well for Tic-Tac-Toe. but I will show you the full version once we finish up here. Here we can see our values are starting to diversify a bit. You can see we also have some negative values, like this one, 20 very high, negative 16 very low. So it seems to be learning. And now we should evaluate how good is it. So what I'm now going to do is say, okay, you have trained for 1,000 games, or 100 million games. Let's evaluate you. So I'm going to have it evaluate for 10,000 games. I'm then going to say, instead of playing a random move, play the best move. And you can do this by setting the epsilon to 0, such that no matter what the random number is that generates, it's going to play the best move, because it can't be less than 0. I'm going to define a new game, game2, a new game object, just to keep them separate. And I'm going to define my number of wins is 0, my number of ties is 0, and my number of losses is 0. And then I'm going to say play the game. If the winner is recorded as the first player, increment this number of wins I have. If it's the second player, that was a loss, and else they tied, reset. And then finally, I'm going to print out wins, the number of losses, and the number of ties. And so we can see that I will not print out the Q table for this one. So we are training for 100,000 games, and we are then going to evaluate on 10,000 games. I'm going to run it, and it's going to take 2 seconds to think. And there you can see it won 9,700 of our 10,000 evaluation games, tied and never lost, which is really good. We just don't want to lose. Tying is okay. And then you can play around with these values. You can say, well, I don't have 2 seconds. I can only train for 10,000 games. And run it, and you can see it did a bit worse. If you train for 1/10 of the time, it loses. It ties a lot more. We can also go the other way and say, well, I have about 15 seconds. Let's train for 500,000 games. And give it a second. And once it finishes, there it goes. So it won a bit more, it tied about the same, and it didn't lose. Pretty good. You can also play against it. Once it's done with all of this, you can then set this player to be random, or you can define a new game with a human player, and there you can play against your super trained AI bot. And that's pretty much it. We've created a bot that's using Q-learning. It's recording all the game states, it's figuring out what the best moves are, and you can see it wins 97% of the time. If you want to get this higher, then you should look into the actual way to update a Q table, which I have copied over here. I'm going to copy it over. There it is. So this new function, and I'll label them new version, this has 2 other parameters, alpha, which it says is the learning rate. This is how fast those rewards are going to update. So you saw when we were printing out our Q table, we were reaching into the 20s. With 500,000 training games, that could reach into the thousands. This is just making sure those don't explode too quickly, and making sure your bot doesn't discover some strategy and shift its whole strategy to that the lower the learning rate is, the slower it's going to update its Q values overall. So it's going to be more stable, but it might take longer to train. And then this gamma value is helping it so the older decisions you make aren't updated as much as the newer decisions. And what I mean by that is if I gave you this board and said make a decision, you could say, well, this is probably a good one, this is a okay one, this is good. Whereas if I gave you this board, X, let's go here, XOX, and then ask you to make a move, you could say, well, this one's probably good, moving as O. With fewer decisions, the amount of reward we want to give to the agent increases because we're closer to the final state of the game. So we do the same thing, we loop through all of our states, but this time, instead of just adding a reward, we're going to get what we expect the maximum reward to be, and then we're going to update our current reward using this complex formula. So we're going to multiply the learning rate by the reward we're passing in plus gamma times what we expect to get minus what it currently is. And all of this together updates it so the rewards, so the Q values are going to stay around from -10 to 10 instead of going to the hundreds like ours were, but it also does make it a bit smarter. And I believe, yeah, we can see that if I'm going to copy this just so we have it and put it as a comment. If we rerun this using our updated Q function, which means I have to comment the old one out, this should take 15 seconds again. Using our new Q function, our rewards are going to be a bit more stable, and in theory, it should perform a bit better. And in actuality, it did slightly worse. So sometimes it doesn't help to use the updated Q function. You can go up to 1,000,000, which I'm going to do. I'm also going to increase this to 100,000 evaluation games, and we're going to see what it does. I might cut the video just because this should take 30 seconds or so. There we go. After training for half a minute with 1,000,000 training games, our bot wins 97.3% of the time, ties 2.6% of the time. Very cool. You can also put them against each other. You could say, well, I'm going to put two of these learning bots against each other. It will be a bit slower because now both of them have to update their Q tables, so training is going to take a bit longer, but we will see. Maybe they'll tie like 98% of the time. And there we go. It actually still won 98% of the time. All right. Thank you for, if you've made it all the way here, thank you. I hope you've learned something about Q learning. I hope I didn't go too fast. If you would like this code, just let me know in the comment and I will provide it. Otherwise, I hope you have a great day.